It's my pleasure to introduce Tiffany Frierson. Tiffany has been a member of Project Icarus ever since the beginning. She's been she's been one of our most consistent supporters and researchers. She's worked on antimatter propulsion, a lot of the advanced concept stuff, but she's always fearless in pitching in and contributing with Project Icarus and the fusion designs. We really are indebted for like almost 10 years of working with you. And she really did rise to the occasion with this conference, just to be here tonight after all the troubles that she had. But she's also delivering an excellent talk that I'm really looking forward to hearing about, which is on the case for doing breakthrough propulsion studies on the moon and why that may be desirable.
Okay, great. I'm Tiffany Frierson, and I'm a student researcher with Icarus Interstellar at Andrea State. And the theme for this year's Starship Congress is what does the moon mean for Interstellar? So I just wanted to tie on the previous amazing talks by Dr. Alcubierre and Dr. Oversee, and try to make a case for a faster-than-light or breakthrough physics lab on a moon base should we begin to go back to the moon. All right. As we know, there are two classes of faster-than-light, or methods for faster-than-light flight, or two solutions to Albert Einstein's general theory of relativity or relativistic equations, and they are warp drives, or Alcubierre drives, and wormholes. So, what do we know about warp drives and wormholes? Well, after the two wonderful talks, we know plenty about warp drives. And I did want to talk a little bit more about wormholes, but yeah, I didn't get a chance to gather more information about those. But they are basically tunnels, hyperspace tunnels, either between distant areas of space or even different time periods, such as between the present and the past. Different examples in science fiction are the Stargate from the Stargate series, and even the wormhole from Star Trek Deep Space Nine. Right, Deep Space Nine. So, okay, so we know that both forms of faster-than-light technologies will require exotic matter. One of the differences between normal matter and exotic matter, that normal matter obeys the standard energy conditions goodness. Sorry, I didn't get a chance to prepare much for this speech, but weak energy, one of the energy conditions that must be obeyed by normal matter is the weak energy condition, or that the actual energy density of matter must be algebraically positive or equal to zero, and that the internal pressures of the matter must be greater than the energy density for any form of matter, really. And the null energy condition, which is really just an extension of the weak energy condition, is that the energy density for any matter, any form of matter, must be greater than or the internal pressure must be greater than the energy density for a piece of matter, which is okay, I can't figure out the word, but it's represented by the equation up there. But it doesn't matter, or the matter that, or energy or matter that must be made for a faster than light space-time to bring about a faster than light space-time. But the energy density, actual energy density, may be algebraically negative, or actually the pressure could actually, energy density could actually be greater than the internal pressure. Am I making any sense? I hope so. So, from the previous talk, we do know that negative energy is actually allowed by quantum field theory, though not by any of the theories of relativity. And actually, from quantum field theory, we know that negative energy densities are actually inevitable. Dr. Overton said the quantum vacuum is actually occupied by virtual photons popping in and out of existence. And as the photons pop in and out of existence, the quantum vacuum algebraic at the average energy density for the quantum vacuum is vanishing, right? But as the virtual photons pop in and out of existence, the energy density of the quantum vacuum can be positive, then negative, then positive again, so that the average energy density is vanishing. Does that make sense? I sure hope so. We know that electromagnetic and other quantum fields can be squeezed. And what that means is that because of the quantum the uncertainty principles for quantum mechanics, we know that if you focus on one quantum property such as energy, it's a quantum. Sorry. Okay. From the uncertainty principle, we know that if we are observing a quantum system, and if we are observing that quantum system's energy, for example, then we can't know its exact position. But according to quantum field theory, we can focus on the quantum system's energy, for example, but we know even less about the quantum system's position or energy, for example. We also have examples of negative energy found in nature. One would be the squeezed quantum vacuum states that I tried to explain a little bit earlier. But there's also the gravitationally squeezed vacuum zero-point field. The zero-point field is basically the quantum ground state quantum field. And there are theories that around large astronomical bodies, the gravitational field actually drags the quantum vacuum along with it, forming a which affects the which affect the actual expectation value of the quantum vacuum. I'm not doing very well. Thanks, but actually, in the last talk, Dr. Oversee spoke a lot about the Casimir effect between two conducting metal plates, or two perfectly conducting metal plates. And so I'll go ahead and skip over that part for a little bit and focus on generating negative energy in the lab. Basically, we have different experimental apparatus, we have different experiments going on in different labs now, but whose goals are to generate negative energy in the lab. We have the Casimir effect with two conducting plates, and one of the main people who are conducting that experiment is Dr. Ford at Tufts University, and many other people now who are investigating that. And the actual experiments have been run, and we know that anytime you squeeze the quantum vacuum, the normalized energy density becomes negative. So that if you properly calibrate the Casimir effect experiment, then you've generated very little, but you have generated negative energy in the lab. I do know that there are actually experiments being conducted now that use technology to squeeze the quantum vacuum. And one of the ways to do that is actually take a laser light and engineer it so that it only ejects exactly one photon of light at the same time. And if you superimpose the individual photons of light, then you can generate very large field of negative energy density. But one theorized experiment that could theoretically generate a lot of negative energy in the lab because it is scalable is one involving parabolic mirrors. Now the theory goes, when you have a parabolic mirror, you can take say the input is light. You can take all of this light and focus them onto a small point, right? So that the light becomes focused. Now, if you input the quantum vacuum, then theoretically you can take a parabolic mirror and focus the quantum vacuum so that you can squeeze a state so that you can generate a negative energy density. And what's scalable about that idea is that you can theoretically take an array of parabolic mirrors and line them up around a focal point. And if you can squeeze the quantum vacuum and focus it into that little point, then you can then you can theoretically generate pretty large amount of negative energy. I did make a presentation, a much better presentation, by the way, about that a few years ago, where I calculated the energy density that could theoretically be generated using an array of parabolic mirrors, but I didn't get to include that into the presentation. But I did include the reference for that. So you can look at the calculations for that and see that it is theoretically sound. Now to the actual point. Sorry about that, guys. Now, why do we want a breakthrough physics lab on the moon, on a moon base? Why would we want to bother with building a breakthrough physics? Should we get to the moon, go back to the moon, hopefully, right? And we build a moon base. Why do we want a breakthrough physics lab? Well, the main reason is the space vacuum. Well, we know that there are fewer particles of anything in space, right? Here on Earth, you have the atmosphere, you have various human technology blasting particles out and interfering with the vacuum, right? But in the moon, you have less than that. You don't have much of an atmosphere. You actually have a smaller gravitational field. And so the vacuum in outer space is much better. Now, if you're running an experiment with quantum field theory in order to generate negative energy, then you're going to want a great vacuum, right? A very high vacuum, so that you can, to a greater extent, calibrate your experiment, right? And hopefully generate even more negative energy. Well, it's easier to do that in a much better vacuum on the moon than on Earth, because when you're creating a vacuum here on Earth, a high vacuum here on Earth, you're sucking the particles away from space, right? The space in between and the experimental apparatus, right? And you can much more easily do that, and maybe even in a cheaper way, be able to do that on the moon. I mean, in a financial way. It's my point right here. It's easier to engineer a very high vacuum on the moon, so that less fewer particles interfere with your experiment, and you can hopefully more easily generate and theoretically be able to generate a faster than light space-time. And also, we need to be able to engineer these space-times, these faster than light space-time metrics in space. Because, well, if you're sending a spaceship from one part or near Earth, theoretically, to a distant part of the universe, you don't really want to launch that spacecraft on Earth, right? You want to send it to space, hopefully engineer your faster than light spacecraft, and then send it on to whatever destination you're going to send it to. So we need to develop and learn to send out the spacecraft and learn how to use the faster than light space-time metrics in space, so that hopefully you get a lot of use out of the moon base or the breakthrough physics lab on the moon. Thankfully, it's the conclusion for you guys. Well, the moon is a very important step towards interstellar as we're building the technology to hopefully travel to the stars, we would like to a more reasonable near-term goal than straight up going to interstellar is to go to the moon, right? Less money, they're building incremental technologies, and they're learning more and more about how to basically become a spacefaring civilization, right? Well, there are many uses for a moon. That's one of the uses for a moon base, is that after developing the infrastructure on the moon, hopefully it becomes cheaper and cheaper to do that, so that we can develop our spacefaring civilization. What's my second point here? And I feel that a moon base would be an important step to faster than light flight. I would like to acknowledge Icarus Interstellar for letting me do this speech. Hopefully they don't regret it. I'd like to especially thank Mike Mongo, Andrea Steelers, and Damian Churchy for enabling me to get here in the first place. My references. If you would like to read more about generating negative energy in the lab and the current effort to do so, these are basically where anyone should start, especially with the first reference that proved that quantum field theory enables negative energy density naturally and possibly in a lab. Thank you.
Questions?
Yeah, how much equipment is needed for this lab? I know we want to go back to the moon, but can we do it from space? Because you just need a vacuum, right? So,
How much equipment is needed for the moon to do a laboratory on space? It's on the moon. How much equipment is needed on the moon to do a laboratory on the moon?
How much what?
How much equipment?
Equipment? There's going to need to be a lot of equipment on the moon, especially if we want to have a human skeleton out there conducting experiments on the moon. So, quite a lot of equipment. But as with any other technology, the more we work on it, the cheaper it gets. So hopefully as costs go down, we can better defend the establishment of the virtual physics lab in the moon. But a lot of equipment, yeah.
thank you.
Any other questions? All right. Once upon a time, I thought I was bold and brave for standing in front of people and saying that I'm an astronaut teacher about a decade ago. But I never would have the courage to stand in front of a room of space scientists, including Miguel Cubier, Richard Amusi, and sit and talk about quantum physics. So another hand for Tiffany Frierson, please.
I know a whole lot more about quantum field theory than I do, but I just wanted to let you guys know that a lot of experimentation and effort is being made toward generating lots of negative energy and hopefully to finally establish faster than light space times and hopefully start to travel with them.
Once again, Tiffany Frierson. Thank you.